Hey guys, in this particular video I'm going to be solving a really simple dynamics problem using our mechanical energy formula, which I derived in a previous video. Alright, so this is the problem. Let's say that we've got a building like this, and let's say that building is 100 meters high, and let's say that we've got a person at the top of this building, right here, at the very corner, and he or she has a coin, and he or she plans to drop that coin down the side of the building. Right, and my question to you is, what is the velocity of this coin just as it passes the halfway point of this building? So this is the coin just as it's passing the halfway point. And one thing you should know is that the height of this building is 100 meters, and we're saying this person actually drops the coin from rest, so he casually lets it go. So in other words, there's no input velocity here, it's just dropping it from rest. Alright, you might want to pause this video to try and figure it out yourself, and then when you're done or you get stuck or whatnot, just unpause the video and see how I do it. Alright, well first, let's get started. There are two ways you can do this, using Newton's laws and acceleration is equal to dv dt. You can do that, but in this particular video, I'll be focusing on this particular formula to solve it. Your change in mechanical energy is equal to your work done by non-conservative forces. Alright, well let's see if we can use this formula here. What's our first step? Like any dynamics problem ever, our first step is always to draw a free body diagram. So this is our coin at some point mid-flight. The only force acting on our coin is going to be the force due to gravity, right? And we'll have a magnitude of mg and we'll be facing downwards towards the ground, right? Not only that, but in reality you're going to have some resistance force due to the air facing upwards, but I'm going to assume that's pretty much negligible in this particular case. And because I've assumed that the resistance or friction due to the air is negligible, that means you're going to have no non-conservative forces acting, meaning that this term is going to be equal to 0, right? Because the only force is mg, which is a conservative force, as I've talked about in a previous video. So there's not going to be any other forces acting, so this force is going to be equal to, so this work term is going to be equal to 0. What does that mean? That means that your change in mechanical energy now is just going to be equal to 0. And you can remember that the mechanical energy has been defined as your kinetic energy plus your potential energy, right? Right? That means that your change in mechanical energy is going to be equal to your change in kinetic energy plus your change in potential energy. If that's a little bit confusing to you, I recommend you watch my previous videos. Alright, well what's potential energy defined as? Well, let's just leave kinetic energy where it is at this point. What's potential energy defined as? Well, potential energy is your gravitational potential energy plus your elastic energy. So that means your change in potential energy is going to be equal to your change in gravitational potential energy plus your change in elastic energy. Now, albeit there could be more potential energy terms in here, but for our simple first year dynamics course, this is all we're going to be covering. So this is potential energy right here. Potential energy, for all we're concerned, will always include just these terms right here. Alright, and that's going to be equal to 0. Alright, well let's see if we can figure out what this term right here is. EE, our change in elastic energy. Well, there's going to be no spring force acting on our coin at any point during our flight, right? There's no springs attached to this coin. This isn't a yo-yo or anything like that. So our elastic energy is going to be equal to 0. Our change in elastic energy is going to be equal to 0, right? Consequently, now we can simplify this expression even further, saying that our change in kinetic energy plus our change in gravitational potential energy is going to be equal to 0, right? And this is a really beautiful expression now, because we know that our kinetic energy, or a change in kinetic energy, is just going to be a half m times your speed at your second point squared minus your speed at your first point squared, right? And I should mention that there's no rotation in this coin as it's falling. If there was, then our kinetic energy formula will be slightly modified, but I don't want to worry about that too much now in this particular problem. And what's our change in gravitational potential energy? That'll be mg times by your change in height, which is going to be y2 minus y1. y2 minus y1, and that's going to be equal to 0. Alright, well in order to solve this problem now, we need to figure out what these terms are. v2, v1, y2, and y1. And the trick to doing this is to choose where we place our axis. So let's go up to our problem. We can choose to place our axis wherever we want. We can choose to place an axis over here. We can choose to place an axis over here, I hope you get the point. But for simplicity's sake, I'm going to choose to place my axis right here at the midpoint of our object at its second position, right here. Alright, so this will be y, positive y, pointing above the ground as always, and this will be x. Alright, so I'm going to disregard all of these potential places I could have placed my axis, and I'm going to put it right there. Consequently now, if we call this position 1 and we call this position 2, right, what's going to be our velocity at position 1? Well, we know that it's described in the question that we released it from rest, i.e. there's no input velocity. So our initial velocity is going to be equal to 0 meters per second, right? What about our initial position in our y direction? Well, based off where I chose to place my axis, we're going to be 50 meters above position 2, or above our axis. So y1 is going to be 50 meters. 50 meters in the positive y direction, because we chose to place our axis here. And don't forget that I said that the coin is being dropped, and we wanted to figure out the velocity at halfway down the building, so it's 50 meters down. Alright, so y1 is plus 50 meters. What about v2? Well, we don't know what that is. That's what we're trying to solve, so we'll leave that as a question mark for now. What about y2? What about y2? Well, based off where we defined our axis to be, y2 is just going to be equal to 0 meters, right? Substituting all of these values in, we can now solve for v2. And let me do that here. This will be equal to a half times your mass of your coin times by your speed at your second point, which I'll just leave as v2 squared, minus 0 squared, your velocity at your first point, plus mg times by, now what do we say y2 was? That was just 0. And what about y1? That was just plus 50 meters, right? And that's going to be equal to 0. Alright, well let's see if we can simplify this a little bit further. If we bring all this over to the right hand side, we're left with a half m times v2 squared is equal to 50 mg. Alright, multiplying by 2 by both sides, we're left with m v2 squared is equal to 100 times g, right? And if we divide 100 times mg, right? And if we divide both sides by mass, assuming that mass isn't 0, which is a perfectly reasonable assumption to make, right? We're left with v2 squared is equal to 100 times gravity. Alright, well this is quite interesting now. Notice that our masses have cancelled off, meaning that it doesn't matter whether this coin weighs 100 grams or 1,000 kilograms, the result will always be the same, assuming you neglect friction. Alright, well now that I've taken that slight detour, let's get back to the problem. Let's try and solve for v2 squared. Well, if we square root both sides, we're left with v2 is going to be equal to the square root of 100g. I should really say plus or minus the square root of 100g. But notice that the plus or minus really isn't relevant here, because as I've derived in a previous video, this term is just the magnitude of your velocity vector, right? It's the magnitude. So in other words, plus or minus really just hints at direction. So it's really unimportant to put this plus or minus here. I mean, just think about it logically. I mean, I can say walking 5 meters in some random direction is just as useful as saying walking negative 5 meters in some random direction. It's meaningless to have the plus or minus here because they denote direction, but v right here is a magnitude. So in other words, your magnitude of your velocity vector is going to be the square root of 100g, right? And we can use common sense now to figure out that our velocity vector at our second point, knowing that our magnitude is the square root of 100g, is just going to be equal to negative times the square root of 100g times by your j unit vector, right? And this may be a lot to swallow at this point, but all I'm saying now is, using common sense, we know that our velocity at our second point will be going down, right? That shouldn't be too surprising to you. It's accelerating due to gravity and it's heading downwards. and we know the magnitude of it. So combining these two things, we know the direction and we know the magnitude. So we can figure out that our magnitude is going to be the square root of negative of 100g, right? And because it's heading downwards, we're going to have a negative here. And j just indicates it's in the positive y direction. Alright, well, we can simplify that a little bit further. We know that's just going to be equal to negative 10 times the square root of g, and whatever that number turns out to is what our is our answer to our velocity vector at our second point. Alright guys, I hope that makes sense to you guys. In another video, I'm going to cover a slightly harder problem, covering a whole bunch of different topics and how to introduce different forces into these types of problems too.